Okay, so we looked last week. We talked about limits. We got our introduction to limits. We talked about what they are, how we represent them, and we evaluated some limits. But the techniques we used for evaluating limits were not algebraic. They were using tables and graphs, right? So the next step is we want to look at how can we evaluate limits. In calculus, we'd say, how do we take limits? This is kind of, you take a limit, you figure out what the limit's approaching, but we're really just evaluating limits. How do we do that analytically? So how do we not depend on technology? Can we just do it with paper and pencil and come up with an answer? Okay, so that's what we're going to launch into today. So before we do that, let's look at the easiest types of limits to take. Like for example, what if I want to take this limit right here? Find the limit, evaluate the limit. What's the limit of this function, 4x squared plus 3 as x approaches 2? Anybody want to suggest a way of doing this problem, maybe?
Plug in 2 for x.
Yeah, plug in 2 for x. Why not, right? Think what you're doing if you plug in 2 for x. If I graph this function, which we can do, I guess they don't have a graph of the function, but if I graph that function, it's just going to be a parabola, isn't it? Right, it's a quadratic function. As x approaches 2, we're just going to be approaching a specific point on the parabola, right? Now, remember, the limit doesn't really care what happens when we get there. It just wants to know what is the trend, right? As we approach 2, what's the value we're approaching? But for a problem like this, it's pretty simple, because the value we're approaching is the value we would actually get to if we went there. You can see my point? If we use the ant model, if the ant's walking along the function, the ant anticipates stepping on the very place that he actually will step. And so the easiest way to figure out where the ant anticipates stepping is just to find that point, right? And that's easy to do by just, we call this direct evaluation or direct substitution. You plug in 2 and you get an answer, right? And so if we do that, if we plug in 2, we just get 19, right? Okay, now there are a whole slew of properties associated with this that I would put under the category of just common sense stuff. You don't even almost bother yourself with, right? For example, there's, this always shows up as a theorem in calculus books, and it's important, but it's also stuff that's really just you would get. If we use direct substitution for these well-behaved functions where the ant's going to step where he thinks he's going to step, here's some basic limits that are always going to be pretty easy. Like, what if we're going to take the limit of b, where b is a constant, as x approaches c? Think about that in terms of a graph. What would the function f of x equals b or y equals b look like? So we're looking at example 1 here. How do I graph y equals b if b is a constant? Horizontal straight line, isn't it? Wherever b is on the function, and let's just say it's right here. If those are the coordinates 0, b, then that's our function, right? Y equals b, or f of x equals b. Does it matter what x value the ant is approaching? In this case, what y value is the ant always going to approach? B, right? Makes sense. So you can think of it from a graphical perspective. He's walking along a horizontal line, his y value never changes, and so the answer is just b. Okay, the other way to think about it is, and kind of taking a little bit more of an algebraic approach, if I'm going to use this technique of direct substitution that we just introduced, I'm going to plug x in, I'm going to plug c in for x. Are there any x's? Yeah. So substitution's already done, the answer's b. Either way, make sense? So in other words, the limit of a constant as x approaches any value is the constant every time. Okay. Once again, it's just kind of common sense, but it is, it is a theorem. What about the function y equals x, right? Because we're taking the limit of the function x, f of x equals x. Well, isn't that just a line with a slope of 1 going through the origin, right? So it just looks like that. every point on here, like if I go out to the point x equals 10, what's the y value? 10, right? So if I go out to the point C, the coordinates are just going to be CC, right? So in a graphical sense, yeah, it makes sense. We're always going to go up as far as we go over. But do we even really need to state this one? I'd say no, because if I just use direct substitution, if I'm plugging in x for c, or c for x, sorry, I get c for my limit. Once again, big deal, waste of time. And then they throw this one into, which follows our strategy of direct substitution as well. If we're taking a power function, the limit of x to the n as x approaches c, you're just going to get c to the n, aren't you? So that's like that page we could just pretty much skip. And this page is more of the same. This is just telling us some things. If we're taking a limit, let's just say we're going to define these limits. If b and c are just some real numbers, and the limit of the function f of x as x approaches c is the number L, and the limit of the function g of x as x approaches c is the number k, then these all are going to make sense. This is the scalar multiple rule. If I do the limit of b times f of x as x approaches c, by direct substitution, aren't I just going to get b times L? Everybody see that? So what that implies is, about the algebra, and we do this a lot in calculus, if we have a scalar multiple, if I'm multiplying some constant times a function, and that's inside a limit, if I'm taking a limit of that product, you can always just take the constant and pull it out in front of the limit and multiply it by the result. Okay? And it's what you would do anyway naturally, I promise you. Okay? Questions? Okay, an example of that would be, let me just show you one real quick. So what if we had, like for that one, what if we did the limit of 2 times x plus 3 as x approaches 4? Well, you could just plug 4 in and get an answer if you wanted. Or if you could also think about it as pulling the 2 out in front and writing that as 2 times the limit of x plus 3 as x approaches 4. Either way, right? Not a big deal. Okay, some are different. If I'm taking the limit of, if I'm taking the limit of the quantity f of x plus or minus g of x as x approaches c, well, I'm just going to take the limits individually. I could break it up into separate limit statements if I wanted to. All that same, no big deal. Product. If I'm taking the limit of the product of f of x times g of x as x approaches c, I could just evaluate directly and get L times k, or if I want to, I could separate that into the limit of f of x times the limit of g of x. Does it make any difference? No, it really doesn't. Same thing for a quotient. Okay. Same thing for a power. Okay, you get the point. We could, if I'm taking the limit of f of x to the n as x approaches c, I could think about that as being the limit of f of x, that answer taken to the n. Is this anything profound? No, not at all. If I told you anything you don't already know, not really. Okay? Why did I have this up here? Oh, I was just reading. Let's get that.
Mr. Cooper, could you dial 3801?
So,
Mr. Cooper, 3801.
Polynomials. What do you know about polynomials? Let's just take a quick, polynomials are a really important thing in math. A lot of what we really use math for is creating mathematical models for applications, biology, physics, economics, whatever. A lot of times we like to use polynomial models because they're easy to work with. They're very well-behaved functions. Get it all squared away?
Yeah.
Perfect. Thank you. Polynomials, are they, what do you know about the graphs of polynomials?
They're not a straight line.
They're not a straight line. Yeah, they do all kinds of dipsy doodles and curlicues and whatnot, right? They're nonlinear. Okay, what else? Are there any places where polynomials might be undefined? You're right, nowhere. Polynomials are defined everywhere, right? And think about why that is. What are the only two danger zones if we're working within the realm of real numbers? What are the only two no-nos for real numbers? You can't divide by 0, and you can't take an even root of a negative number. Do you see any variables in the denominator or radicals here? No, right? Polynomials are nothing to worry about. The domain is always going to be all real numbers, okay? So because of that, we know that if we're dealing with polynomials, I can always, just immediately, if I'm taking a limit, just use direct evaluation, right? And we're just going to take the limit term by term. What that means is if I'm taking the limit of a polynomial that has a whole bunch of terms, just deal with each term independently. Big deal, right? Easy to do. Same thing is true for rational functions, as long as you're not dividing by, it's not a value of x that's going to make the bottom 0, right? So if a rational function, and remember, what's the definition of a rational function? It's a ratio of what? Is that not ringing a bell? It's a ratio of polynomials. That's the definition of a rational function. It's a ratio of polynomials. Okay. So you know that because each of the polynomials is okay to take the limit of using direct evaluation by themselves, so is the rational function, as long as it's not some value that's going to make the bottom 0, because that's forbidden, right? But as long as the bottom's not 0, just plug in the value and see what you get, okay? Same thing for radicals, right? You can just apply, their radicals are going to be defined every place in their domain. So as long as the value of x is in the domain of the radical, plug it in. Okay, now we're getting on to something maybe a little more interesting. Compositions of functions. Okay? It's going to work for any composition of a function as long as you're not violating one of those two rules. Right? So if we're taking something like, for example, let's say we've got the square root of x squared plus 4. Right? That's a composition of functions. I'm taking the square root of a polynomial, right? So we know that if I want to evaluate this, as long as I'm picking a value of x so that the output of the polynomial is not giving me a negative number, I'm fine, right? I can just attempt direct evaluation. Yes, sir?
What if it does give you a negative? Then what do you do?
Then
complex?
things blow up, because in that case the limit wouldn't exist, right? So the answer would just be does not exist because the function's not defined there, okay? Now, if we want to look at this within kind of a mathematical context here, we could say for compositions of functions, if f and g are functions, and we're going to say that the limit of g of x as x approaches c is L, and the limit of f of x as x approaches L is f of L, then we can create a composition of these. We can do f of g of x, right? If I take this limit. Now, if I'm taking the limit of f of g of x as x approaches c, well, when we're evaluating a function, you're always going to evaluate a composition of functions from the inside out, right? So we'd plug the value of c into g of x, right? And so we're going to get the limit of, first we're going to do the limit of g of x. The limit of g of x as x approaches c is L, right? And so then our final answer is just going to be whatever the function is evaluated at the output of g. Okay, so let's go down and look at our example down here. Now, sometimes when you look at the very general abstract theorem, it's a little bit harder to see than when you apply it to an example. So now when you apply it to an example, you'll see what I mean here. It's no big deal. If we're going to do, like, let's look at the limit of the square root of x squared plus 4. If I evaluate this when x equals 0, I'm just going to get the square root of 0 plus 4. So the square root of 4 is 2. It works. We would have had a problem, though. Actually, we wouldn't have had a problem in this one, no matter what. Could I ever have a problem? X squared plus 4 is always positive valued, isn't it, that expression? So we're fine there. But what if that had been a minus 4? Right? If that had been a minus 4, x squared minus 4, and I tried to plug in 0, I'd get the square root of negative 4, which is non-real. So the limit wouldn't exist. Okay. Make sense? Okay? All right, and then this works for all the trig functions too. Okay. So that's a lot of talk about very little, right? Very little. We just know that when we're evaluating functions directly, if it works, great. Okay? And in fact, when we try to evaluate directly, there's really three kinds of results that could happen, and that's it. We're going to try to plug direct substitution. The first one is the best, the easiest. If we try direct substitution and we get some answer that's a rational number, it might even be irrational, right? This doesn't necessarily have to be a rational number. It could be pi over 2 or something crazy like that too. But we're going to get some answer where we're not dividing by 0, right? So it's not some, it's a legal, real number. We're done. Direct substitution worked, and that's our answer. And the examples we've looked at so far today have all fallen under that category. Direct substitution works, and you're done. Okay, there's two other things that could happen. One of them is, and all the previous examples were that. The other thing that could happen is we could get an answer where we get a number divided by 0 when we try to use direct evaluation. Okay, and here's an example of one like that. What if we tried to do the limit of the function x minus 5 over x plus 2, move this up a little bit, as x approaches negative 2. When I try direct substitution this time, I get negative 7 divided by 0. Well, we know we can't divide by 0, right? And so for now, that just means does not exist. The limit doesn't work. Soon, we're going to look at being a little more descriptive about that. When you get one like this, where you get a number divided by 0, what do you think is probably happening to the graph of the function? What do you think? Any ideas? You can be wrong. The wrong answer gets us talking.
It's like an
So it's a gap, or like the world's goes up.
Ah, there you go. So it's going, that's the key. It's going to be either up or down, but it's going to be an asymptote in the function, right? There's going to be this infinite split in the function where you get this infinite behavior. The function's going to plunge down to negative infinity or rise up to positive infinity as we approach that value. We'll discuss that in a lot more detail in the near future. But for now, we're just going to say it doesn't exist. In the future, we'll look at maybe saying, okay, well, it doesn't exist, but that doesn't help us very much. Could we know more about it? Yeah, we could. What if we approached negative 2 from the left or the right, and then we get answers like if we approach from the left. What if I approach negative 2 from the left, and the answer is positive infinity? Then that means, thank you, that means as I approach from the left, the function's going to be rising up to positive infinity, which might be really important to know about the function. Let's just say hypothetically that when I approach negative 2 from the right, the limit ends up being negative infinity. And we'll talk about how you get those. You don't know that yet, so don't panic. We approach from the right, it's going to plunge down to negative infinity, which is more useful than just doesn't exist. It actually tells us what's it doing. It doesn't exist, but what's it doing asymptotically. But for now, we're going to be satisfied to just say if we get an answer where I get a number divided by 0 when I try to evaluate the limit directly, we're done. The answer is does not exist, no limit. Okay? So we got those. Those are the first two possibilities. Either it works or we get a limit that's not defined. It does not exist answer. The third one is the one that we're going to focus on, because those two are both pretty short and easy. Right on your assignment, if you get those, quick, you're done. You try direct evaluation and either you get an answer or it doesn't work. Here's the other possibility. You get an indeterminate form. You get an answer like 0 divided by 0, which is one of many indeterminate forms in math. Now, an indeterminate form is exactly that. We don't know. We don't know what the answer is. We're going to have to do something else, which involves some algebra. Right? We're going to have to do something else to figure out what the answer actually is. So let's focus on, this is the one that's the only one that really involves doing anything, so let's focus on the third type. Okay, so what about something like this guy here? Let's take this piecewise function. F of x equals x squared plus x plus 1 whenever x is not equal to 1. And when x equals 1, the function is defined as 1. If I look at a graph of that, let's see, is there a graph of that somewhere? I think there is, right here, I bet. So there's a graph of the function. Make sense? If we looked at some limits of functions like that last week. Okay? So if we want to find the limit of this function, you can already tell me what the limit is, can't you? The limit of this function as x approaches 1 is what? 3. Good. That's the value that the ant anticipates stepping on. Okay? There's another way we could do this one. We could say, okay, well, we happen to have a graph of the function there, so we can see what's going on. But we could think about this in a different way. We could say, okay, well, let's pick a function that agrees with our original function everywhere except at the one point we're approaching, which we don't care about because we never get there, right? Let's replace this function with this function, right? G of x equals x squared plus x plus 1. Isn't this a case where even though the value of the function at 1 is not 3, we're approaching the value 3. So why not just scrap that function, this piecewise function, and replace it with an easier one to deal with, which is this guy? Because if all we're looking for is the value of the value of the function that the ant anticipates stepping on, why not just pick the function that the ant actually would step on and use direct substitution? You see my point? This is kind of a crazy name for this, but this technique in calculus is called finding two functions that agree at all but one point. That's our strategy. We're going to try to, essentially, we're going to try to fill in the hole where the ant would be, where the ant actually steps. Because what do we care? If we're trying to find the answer to the limit, we only care where he thinks he's going to step. Well, he thinks he's going to step in the same place in either one of these two graphs, doesn't he? It doesn't matter that when he steps there, he actually gets beamed down to this point because the limit never gets there, right? So that's our strategy. The strategy is finding two functions that agree everywhere except at the point that you're interested in. Let's get rid of this thing. Okay? Because they agree every place except at that point, we can apply direct substitution to the one where he actually will step where he thinks he's going to step. Now let's look at a more interesting case. How about something like this? The limit of x cubed minus 1 over x minus 1 as x approaches 1. So try to evaluate that directly. You have to write it down.
Zero over zero.
You're going to get 0 over 0, aren't you? Right. So this is that third case where we get 0 over 0. It's indeterminate form. It means more work. Okay, how do you suppose we might go about doing the more work? Let's just take this example. So let's take the limit of f of x. Could we come up with a function? If I graph this thing, what's that graph look like? There's the function. There's the function x cubed minus 1 over x minus 1. If I graph it, it looks like a parabola with a hole in the function. Okay? What could I do to come up with a function that fills in that hole? That's going to agree with this function every place except at that one point. We're going to be able to fill in that hole so that we could use direct evaluation. Right? If we plug in, if I could fill in that hole so that the ant actually would step there, then I could just plug x in and see what the y coordinate is, right? That's our whole goal. This whole section revolves around that one simple trick. What do you think? What's the algebra look like for that? Can I rewrite f of x?
Yeah.
Okay, what's the top look like? X cubed minus 1 is the same as x cubed minus 1 cubed. Difference of cubes. how do we factor a difference of cubes, remember? It's been a little while.
You did difference of squares.
Okay, difference of cubes. Right? So it's a minus b times what?
A
Squared plus ab.
Oh, dang.
Let's remember that stuff. Okay, I'll show you a trick for remembering this. So here's the way you can remember this. So if you do a sum or difference of cubes, when you're factoring that, you're always going to get a linear factor times a quadratic factor every time. And the terms are always the same. You're going to get an a and a b for the terms in the linear factor, and you're going to get an a squared, an ab, and a b squared for the terms in the quadratic factor. But the signs are what you just have to keep track of. So you know that the linear factor is always going to have the same sign as the original polynomial, right? If it's a sum, then that's going to be an a plus b. If it's a difference, it's going to be an a minus b. And then the next one is always going to flip, so it's the opposite, and the last one always stays positive. Okay? So we could factor the top then into what?
X minus x plus x plus 1.
Good. Okay, now what happens here? Okay, so now let's go back and review from Algebra 2 and Pre-Calc here, because this is a big topic. What happens if I end up with 1 is a 0 of both the top and the bottom? If it's a simultaneous 0, a shared 0 of the numerator and the denominator, what do you know about what's going on in the graph?
There's canceling.
Yeah, but what's going on there? Why hammer this so hard in Algebra 2? What's going on there? If it's a shared 0, it always corresponds to a hole, every time. So that's a hole in the function, right? We know we have a hole at positive 1, because that's a 0 of both the top and the bottom. If it's a unique 0 of the top, so if the top is 0 and the bottom is not, well then the function just equals 0, right? That's no big deal, that's regular. If we have a 0 of the denominator but not the top, so it's a unique 0 of the denominator, that always corresponds to a vertical asymptote every time. Is that ringing a bell?
Yeah.
Okay, good. All right, so you know we've got a hole in the function here at 1. Well, what do you suppose? Oh, there's our hole, right? See what I'm saying? So if we were to algebraically cancel the x minus 1s, we're going to come up with a new function that fills in the hole. Okay, but I want you to remember here, though, this is important. It seems like it's just a little fine print at the bottom of the contract. But if I cancel the x minus 1s, I'm actually changing the function, aren't I? It's no longer f of x because I filled in the hole. So technically speaking, we would have to call that something like g of x. If I cancel the x minus 1s. Right. But now I could directly evaluate that, couldn't I? Right? If I evaluate this, so now I could say the limit of g of x as x approaches 1 is just going to be 1 plus 1 plus 1 equals 3. You get that? And so what this amounts to then is we're going to fill in the hole and pick a new function that's easy to evaluate, because now the ant is going to step where he thinks he wants to step. And by directly evaluating, we get the answer 3. So what does the calculus look like then? Because let's streamline this a little bit. We started off with f of x, we canceled the x minus 1s and created this new function that we're able to evaluate directly. Well, here's how you can show this and be correct in your work in terms of calculus. The limit of x cubed minus 1 over x minus 1 as x approaches 1 is equal to the limit. Now notice I have to drag this limit notation with me the whole time because I haven't evaluated or taken the limit yet. So that's equal to the limit of x minus 1 times x squared plus 1 all over x minus 1, which is equal to the limit of x squared plus x plus 1 as x approaches 1. So I can algebraically cancel those offending factors and fill in the hole. Did I have to specifically state that this is f of x and this is g of x? No, because their limits are the same, right? That's the whole point, their limits are the same. So without having to specifically define this new thing as g of x, I know that the limit of the purple function is also equal to the limit of the red function, right? And now we can just directly evaluate and we're done. Our answer is 3 when we evaluate directly. Okay? So we could call this like a cancellation technique. If you've got a rational function, ratio of polynomials, and I've got an indeterminate form result where I try to evaluate directly and I get 0 over 0, this technique will always work. Okay, try one. Try that one real quick. In this book, they call it the dividing out technique. That's fine. Cancellation technique, dividing out, whatever. Did you get an answer? What'd you get?
-5.
-5. Sounds good. Okay, how'd we do it?
Factor.
Okay, but first,
First you gotta plug it in.
Direct.
okay, first we're gonna try direct substitution or direct evaluation, but we get 0 over 0. Good, so we gotta keep going, right? And this is one where we have a rational function, so we know we're gonna be able to use our dividing out technique. So it equals the limit. And when I'm grading your work on a paper and pencil test, if you don't say limit there, that's a mistake, right? We're still taking we haven't evaluated the limit yet. It's the limit of, what does the top factor into?
X plus 3 times n.
Good. And you could have, without even, I mean, like if you're having trouble factoring it, what's one factor that you know has to show up on the top? X plus 3 has to be there, because that's how we're gonna get that 0 over 0, right? So that's gonna equal, if I cancel the x plus 3's, it equals the limit of x minus 2 as x approaches -3. If I directly evaluate that, I get -5. Done. You got it. Okay, good. All right, so there's the work you just did. And once again, just to kind of reinforce this, we just filled in a hole, didn't we? Right? Okay. Okay, so, that's the end of the line. What are we out of here? 25. Okay, I'm gonna throw in one more. It just seems to fit today. I'll throw in one more quick example here. So what if, so if I'm taking the limit of a rational function and I get an indeterminate form, I just use that technique. What about, here's a good example. Oh, here's one. Yeah, what about something like this? Okay, that is clearly not a rational function. That's what we'd call a complex fraction. Fractions within fractions, right? Okay, what's my first step? Anytime I'm taking a limit. Direct substitution. If I try it though, what do I get? 0 over 0. So we gotta do something here too. This does not look like a rational function, but could we make it look like a rational function? Yeah, we could. All this amounts to is just simplifying this complex fraction until it turns into, you know, a fraction over a fraction, or a polynomial over a polynomial, something like that. Right? So how do we simplify, and this goes once again, did I not tell you? I mean, this is mostly algebra. You'll do more algebra this year than you've done your entire life, I promise you, in one year. How do we deal with simplifying a complex fraction?
You multiply by 6.
Okay, so, right, we could multiply by 1 over x. You're right. But this part on top up here, that's kind of a problem. And we have to just simplify that fraction. We got to get a common denominator, and we have to kind of power through it a little bit here. We just have to simplify. Our goal is, whenever we're simplifying a complex fraction, what we like to do is turn the top into just one big fraction, the bottom into one big fraction, and flip and multiply by the bottom, right? So let's focus on the top. The bottom's already done. Bottom's a piece of cake, but the top is not. So in order to deal with that, I've got to get a common denominator. What's my common denominator going to be?
2 plus x.
2 plus x
Times 2.
times 2. It's going to be the product of the two denominators, isn't it, in this case? So I'm going to have to multiply the first fraction in order to get my common denominator by what?
2.
2 over 2, right? Top and bottom by 2. So we're going to multiply this guy by 2 over 2. What about the second one?
2 plus
There you go. Good. So multiply this one by 2 plus x over 2 plus x. And so that's going to give us the limit of something better. So I know here I'm going to get 2 over 2 times 2 plus x minus minus 2 plus x over 2 times 2 plus x. Common denominators, all over x, right? Which equals the limit of, well, now I've got my common denominator on the top. So all I've got to do is combine the numerators, right? So the numerator on top is just going to look like all that stuff, right? It's going to look like 2 minus the quantity 2 plus x. And what's that simplified to? 2 minus the quantity 2 plus x is what? Good, negative x? Negative x over 2 times 2 plus x, that fraction divided by x over 1, flip and multiply, right? So that's going to give us negative x over 2 times 2 plus x times the reciprocal of the bottom is 1 over x. And what do you know? It's factored. The x's are going to cancel, aren't they? Right? And then we'll be able to evaluate directly when those x's cancel. Okay? See the point? Okay, good. There's a new assignment going up. You can start it.
But hold it,
Okay.
that's an opposite